Hello, welcome to video number 11 in atomic physics, half-life, which again will be recapping what we did in physical science. So it's very much a condensed version of what half-life is about, and so I won't go into nearly as much detail. If you want to know more about half-lives, bit more talk through it, probably go have a look at the physical science video on half-life. But this is just a recap, just to bring you up to speed. And just to remind you, the half-life of a radioactive isotope / atom is the time taken for half of its atoms to decay. And typically you'd see a graph like this where you have time, in this case it's in minutes, number of nitrogen-13 remaining, so starting off with 10,000, which is an unrealistic number, but that's just what we're doing. Remember also that these axes, particularly this one here, can have a whole variety of things, from percentage remaining, to fraction remaining, to activity, counts per second, counts per minute, counts per hour. But here we're starting off with an imaginary 10,000, and the half-life would be for it to decay so that there's only 5,000 remaining, and here it is here, looks like it's 10 minutes, so in another 10 minutes half of that amount again will decay, and half again. So this line is trending towards zero but not reaching there, and that's your typical half-life graph. We get a lot of questions where half-life is given to you and you need to work backwards or forwards. And basically you're doing a calculation based on the visualization of that sort of graph. When we do the next video though, we'll start introducing some calculations. In physical science the half-life is pretty much nice and sweet, but how do we work out the activity there or there when it's not exactly a half-life? And that's what we do in physics, so that will be coming up shortly. I think I've got another graph here. And this is one I hadn't seen before, or had seen but hadn't included in the physical science section. Something I talked about though. In this case we've got number of half-lives, 1, 2, 3, 4, 5 there. Proportion of parent, so you're starting off with 100%. And on the graph you've also got the proportion of the daughter. So as the isotope is decaying, the percentage of the daughter is actually increasing correspondingly, and we talked about that, but we probably didn't graph it and certainly didn't show it like this. So let's move on. Now here are some half-lives, just to give you an indication. Again, we talked about this in physical science, but if you haven't remembered, half-lives can range from anything down to tiny little fractions of a second, as is the case for polonium 124. What else have we got here? Polonium 214, sorry. Up to billions of years. And although they've got different, like this is uranium 234, has 4.51 billion years as a half-life. Uranium 238 is 4.47 billion years. So each isotope, the point here is each isotope has its own unique half-life, and that comes from the decay constant, which is again something we'll be looking at in the next video. So just showing you the range. And so when we're using isotopes, be it to date rocks or to look at the uptake of nutrients in plants, scientists would pick or use the isotopes with the half-lives and the chemistry that's most appropriate to you. And not all the isotopes are used for scientific studies or medicine, but an awful lot are when you explore it in a bit more detail. Now, decay series is something we mentioned in physical science, and that's through by emitting a combination of alpha, beta and gamma radiations, atoms gradually change into new, lighter, more stable elements. So this is talking about the heavier part of the periodic table, where elements are trying to rise. Remember that hump that we had in the previous sections when we talked about nuclear stability? So this is what heavier elements are trying to do is they're trying to go from heavy elements down to more stable elements and reach a zone of stability. And this is an example of uranium-238 going down to lead-206, that says. And this little key here shows you for what sort of jump you have, where we have atomic number down here and atomic mass here. So if you undergo alpha decay, it jumps like that, beta positive and beta negative. So the atom comes down here, and sometimes there's a choice, depending on what the atom decides. Again, it can decay in a variety of ways, but the end point will always be the same, and that's a decay series. And so I think I've included in your OneNote a sheet where there's just an example of a decay series. This is again uranium-238, just another diagram showing the same thing, but a little bit prettier. And they've only included alpha and beta decay, not to confuse you. So this is the sheet that you have in your OneNote. It continues on, and we did this in physical science class if you had a chance to do it. So it's a bit of practice, remembering with nuclear reactions the top numbers have to equal. So this 234, the top numbers have to add 234, and the bottom numbers have to equal as well. A little bit different from chemistry. And you should now be able to do the set 15 questions in your workbook. Now in the next video we'll look at the laws of radioactive decay, which is pretty new stuff in the course for